Hello students, welcome back to Physics 110 Lab. Today we're going to be learning about the Eratosthenes method. And what this method does is allows us to find the radius and from that the size of the Earth. So a bit of background as to Eratosthenes. He was a Greek mathematician and more than a mathematician, he was a philosopher, all sorts of other things, artist, poet, things like that. But basically he was a scientist in the Greek world around 276 BC to 194 BC. He made several large contributions to science as a whole, but the best known one for astronomy is helping to calculate the size of the Earth and actually doing quite a good job at it. So he came up with this method, and then not too long later this method was improved upon, and then not too long after that the method was made much, much worse, and that is how later astronomers got wrong ideas about how big the Earth was. So around this time, the philosophers of the day did know that the Earth was probably spherical, and actually they thought it was perfectly spherical, which is one misconception that was changed going forward. Now they didn't quite know exactly how the solar system worked, but the idea was that the moon was away from the Earth and the sun was further away than the moon. And whether the sun rotated around the moon, or rotated around the Earth, and the moon rotated around the Earth, as well as the stars in the celestial sphere, didn't really matter. The fact of the matter was that the Earth was a sphere in the middle. Things happened outside of that, and the sun was pretty far away, but close enough that it could shine on us and make our day light. So what Eratosthenes did was use trigonometry and what we know about circles to come up with a way to find the radius of the Earth. And basically what it boils down to is what's going on here. So this is the sun very far away. As the sun shines and we imagine all of the light comes from a single point, it will shine in straight lines. So light doesn't curve usually. If it goes through something, lenses can curve light, but in general, light goes perfectly straight. Another unique thing that this method took advantage of is if light encounters a curved surface, it will normally curve, but if it encounters it on a path that would lead straight to the center of that curved surface, it doesn't curve. So light is going very straight. So the sun shines, and the sun shines on a path that would lead straight to the center of the Earth, and that goes through the nearest point to the sun. And it also shines, I guess, on the rest of the planet. The half of the planet that's showing towards the sun has light shining on it. And Eratosthenes said that if there was a tower some distance away from, again, the nearest point to the sun would shine on that tower and leave a shadow, and the shadow could be measured. And using the trigonometry tricks, we could figure out that the angle between the tower and how the shadow is created, so this angle here from the pinnacle of the tower off this direction, and the angle here between the center of the planet and the line connecting to that tower would be the same angle. We also know that this other angle is a right angle. First, the tower is built straight up, and if the line is drawn from the center of the Earth to any point on the Earth's surface, and then to some other point that is a right angle. So now we know two angles of both of these triangles, and we know that they're the same angles. So this angle's theta, this angle's theta, this angle's a right angle, and this angle's a right angle. What this means is we have similar triangles, and with similar triangles we can make quite a few assumptions and do some relatively simple math compared to what you might need to do using other methods. So Eratosthenes decided and proved that if you know the height of the tower to a very accurate measurement and you know the length of the shadow, the only really other thing you need to know is the distance between that tower and the point where the sun is directly overhead. So some point on the Earth, the sun would be directly overhead, and if you know that distance, you can now solve for the radius of the Earth, which is this line here. So since it's similar triangles, we can set up this relation here. The height of the tower over the length of the shadow is equal to the radius of the Earth over d, or the distance between those 2 points. So looking at this, we can kind of see what you would need to do next. And that is to find places on the Earth where you can actually do this. So there's a few things you need to be able to do. Basically, it is finding very accurate measurements. This is for your tower, for the length of the shadow, and for the distance between the 2 places you make your measurements, and getting your timing right. So this requires that the sun be directly overhead at one point on Earth, and concurrently at some other point on Earth, you're making a very accurate measurement of how long the shadow is. So what they did was they found a place with a very deep well, and that is in Sienne, Egypt. Basically, there was a very deep well that had very regular sides, and this meant that when the sun was directly overhead, the sun could shine all the way down that well. So it was very easy to tell when the sun was directly overhead. Much easier than if you just sent someone out with measurement equipment to try to figure this same thing out. And directly north, due north of Sienne, Egypt, was Alexandria, and in Alexandria there was an obelisk. So the obelisk was a very tall pointed tower, so you could make a very accurate measurement of how tall it was, and you could also find the point in the shadow and make a very accurate measurement of the length of the shadow. And the distance between these 2 places was 787.5 kilometers, and I believe that is the modern measurement. Eratosthenes may not have had quite as accurate of a measurement. The other important thing is that these 2 are due north or due south of one another. This means that they both experience noon at the same time. So if you were to head east or west of this, the sun would take longer or appear high in the sky earlier in the day. So them being on the same longitudinal line, or the same meridian, is important here too. So Sienne, Egypt was where the deep, perfectly straight well was. So on a certain day, the sun would pass directly overhead. And this is because this well and the city itself existed between the Tropic of Cancer and the Tropic of Capricorn. Again, because of the Earth's tilt, these are the only areas on the planet that will experience the sun being at the zenith. And everywhere in this area will have the sun at the zenith angle twice a year unless you're directly on the lines of the tropics. So on that day when the sun would be directly overhead, it was quite easy to tell when the sun would be at the right spot because you could watch the sun illuminate more and more of the well. So early in the morning, only some of the well would be lit up. And then later the sun would shine deeper into the well. And then at high noon, when the sun had reached its peak in the sky, right at the zenith angle, right at 90 degrees above this well, it would shine all the way to the bottom, and an observer would be able to tell that. So basically all this observer needs to do is say that on a certain day, the noon sun shined all the way to the bottom, and that's how you know that the sun was actually at the zenith angle. And then later in the day, the sun would move off and less of the well would be illuminated. The Alexandria, Egypt was a different measurement. So basically, once you knew the day this would occur on, you would have someone else measure the shadow of the obelisk. So here's the obelisk, there's the sun, and the shadow points away from the sun. Again, timing is important, so the noon shadow length is the important length to measure, but luckily it's also relatively easy to find this as long as you know the day that you need to be making your measurements on. So the sun would never reach the zenith at Alexandria because Alexandria was on a different part of the planet that wouldn't have a zenith or the sun would not appear in the zenith that day because it was due north of where that was happening. So this is the above view. Here's the obelisk looking up. The point would be right there, pointed at us. If the sun rises in the east, the shadow would be very long and heading off to the west. A bit later in the day, the sun would get shorter, but it would still point west and begin to move towards the north. And then at noon is when you would be making your measurement. So you would know it's time to make your measurement for a few reasons. If you knew which direction was due north, you could wait until the shadow pointed due north, or you could wait until the shadow was its shortest length. So if you put a mark every couple minutes for where the point of this obelisk was, you would have some sort of an arc, and after noon, or after the sun reached its highest point, again, the length of the obelisk would begin to grow again. So you would be looking for the shortest length if you had marked all of these points. And then late in the day, the sun would be in the western sky with the shadow pointing off towards the eastern sky. So you could do all of these things. Now you know what day this is happening on, and if you know what day you're making your measurement, you can go to the obelisk and find out the shortest shadow length, which would appear at noon. And from those two measurements, you go back to your geometric argument and you plug in the lengths that you have. And from that, you can find the radius of the Earth. So Eratosthenes calculated the Earth's radius to be 6,267 kilometers, when the actual is not too far off, 6,371 kilometers. So he was very, very close, and he was actually the closest one for quite a while until we developed more modern ideas for how to find the radius of the Earth. Some of his errors came from just not being able to measure the distances as accurately as we can nowadays, and some of the assumptions he made. So he assumed that the Earth was perfectly spherical, which it isn't. It's pretty close, but it's not quite perfectly spherical. Also, there are some approximations that go into making the similar triangles argument that could introduce a small degree of uncertainty into the measurements. Also, he could not calculate the distance between the two cities using any sort of accurate measurement. Even trying to measure them himself, it wouldn't really work. So there are several stories about how he arrived at the distance between the two cities, and those different methods would introduce error into the calculation. However, this was a very good calculation. Later, there were less accurate measurements and calculations that became accepted among the scientific community or the philosophers and the people who were actually using these measurements for navigation and planning trips. And this is one of the reasons that Christopher Columbus thought the planet was much smaller and his trip to India would be easier when he accidentally found the Americas. So, in today's lab, you're going to be following this method. You will have a computer simulation set up that will look very much like the slides we just did. It will be guiding you through a way where you can watch for the sun to shine all the way to the bottom of a simulated well. And once you have that, you can freeze time, and unlike Erasmus, this makes it very easy to get all of the measurements at once, instead of having two separate teams or doing this on concurrent years or some other way where you would need to do this before anything modern in the way of communication or measurement was invented. So I hope you enjoyed today's lab. This is one of my favorite labs that you'll be doing, and it illustrates a very simple way to solve a problem that's actually quite complex. So as always, if you have any questions, ask or email your TA, and I hope you have fun in today's lab.